Today we'll take a look at graphing rational functions. We'll highlight some steps that we can use to do that. It's going to relate to the information we previously discussed with rational functions. We're going to essentially set a denominator equal to 0 to look for the location of those vertical asymptotes in holes. We'll set the numerator equal to 0 in order to determine what those x-intercepts are. We'll let x equal 0 to determine what the y-intercept will be. We'll look for end behavior, so we'll compare the degree of the top and the bottom, looking for whether there's a horizontal asymptote or not. And then that's sort of what we've highlighted already so far. Using those things, we're going to sketch them out on our graph, and then we will complete the graph as necessary. We might choose some other x values, plot some points, whatever needs to be done to determine what's happening, to fill in the blanks between all that other information. So let's try one nice thorough example here. We've got the function x plus 1 divided by x minus 1 times x plus 2. So let's look for first the vertical asymptotes and the holes. Those are the issues that we've talked about with the domain from before. So we're looking for essentially when is the denominator equal to 0. Notice, spoiler, right, there are no holes here. We can't divide either of these two factors out. There's no way to get a simplified form of this function. So we know that they aren't holes. We know they're both going to actually represent vertical asymptotes here. So solve for x in each case, right? X minus 1 equals 0. That's going to give us x equals 1. X equals negative 2 would be the other. And again, since they don't cancel out, both of those are vertical asymptotes. So we'll start sketching our graph with those things in mind. So make a vertical line at x equals negative 2, make a vertical line at x equals positive 1, and we've got the very start of our graph. We know that the graph is going to either go up towards positive infinity or down towards negative infinity on either side of both of those asymptotes. And in fact, since the multiplicity is odd for both of those, we know it's going to be opposites. One side it's going to go up, on the other side of the line it's going to go down. To decide which is which, we'll look at the rest of the information though. So that's our start. We'll look for x-intercepts and y-intercepts. Also, those are going to give us some nice solid points that we can plot on our graph. Going back real quick, remember for x-intercepts we're looking for where the numerator is equal to 0. For the y-intercept we're going to plug in 0 for each of those x's. So let's try that. We've got for our x-intercept set the numerator equal to 0. That gives us x equals negative 1. So we're going to plot the point negative 1, 0 on our graph. For the y-intercept, we're going to plug in 0 for each x into the original function. We're going to get an output there of negative 1/2. So that means that the point 0, negative 1/2 will also be on this graph of this rational function. So that actually helps a lot. So I've got our two vertical asymptotes from before, plus now we've got the x-intercept and the y-intercept graphed on there as well. Remember that these 2 points are going to have to connect, and we know that as we get close to those asymptotes, we get an idea of what's going to happen too, right? Our function is going to have to decrease down here to connect the 2 points, and then off towards negative infinity. On the left, towards that negative 2, it's going to go up towards positive infinity. And furthermore, since we said that those multiplicities on the bottom were odd, we know that it's going to flip. So at the asymptote where x equals negative 2, the other side is going to flip like this. And the asymptote x equals positive 1, the other side is going to go up this way. But we still need to think about what's going to happen to the end behavior. So we do have a little bit more information. We know the graph's not going to cross the x-axis again because we looked for every single x-intercept, every single root, and we only found one. So we know the graph can't cross that line again. So we have a thought that maybe that'll help with the end behavior, but we can analyze it the same way that we did before. Let's look for end behavior and we'll finish our graph. So remember, for the end behavior, we compare the degrees. The numerator had a degree of 1. There's only one linear factor up there. But the denominator had a degree of 2. There were 2 linear factors on the bottom. So what that means is that there is a horizontal asymptote, and it's at the line y equals 0. I'm going to jump back again real quick. That is consistent with what we just said as we were sketching, right? That is the x-axis that we just drew out here. We know the graph is not going to cross that line. So we expect then that our function is going to just level off towards that piece as we go in either direction towards the end behavior. So we'll complete our graph, right? We've got that horizontal asymptote of y equals 0 drawn in. And as we discussed previously, since the multiplicity is 1 for each of those vertical asymptotes, we have opposite end behavior happening. And you can use a sign chart if you need to. I mentioned that in the previous slide, and I included the chart here. We didn't use it when we just made our sketch, right? We had an idea of what was going to happen. But you could also always test each individual factor and see where your function is positive and negative, and then multiply and divide those positives and negatives out to see where your function is going to be positive and negative. Notice that fits, right? Up to the first asymptote, it's negative. Then between the two asymptotes, it's positive. And actually, more specifically, between the asymptote and the 0, it's positive. After the 0, or the root, it goes negative, and then after the other asymptote, it becomes positive again. So you can feel free to use a sign chart there to help. For some more complicated ones, that might be a useful strategy.